In this section, we'll see that slope gives us a rate of change. Now we've already know the formula used to calculate slope is y2 minus y1 over x2 minus x1. But when we do this in an application, our numerator is measured in y units and our denominator is measured in x units. So the units for the answer would be y units per x units. And this gives us the rate that y is changing with respect to x. Now if the relationship between x and y is exactly linear, meaning that y is consistently changing at a constant rate, then we'll call this the rate of change. Now if the relationship between x and y isn't exactly linear, then this still gives us a rate of change, but we're going to call it the average rate of change. So let's see how this works in a real application. Pittsburgh's population in 1990 was 370,000 people, and in 2007 it was 311,000 people. Now let's start by defining our variables. We'll let the independent variable be t, and that's the number of years after 1990. And the dependent variable will be p, representing Pittsburgh's population measured in thousands. Now the information really gives us two different order pairs because we know that in 1990 the population was 370,000. So in that year t would be 0 because 1990 is 0 years after 1990, and the output would be 370. And then we also know in 2007 it was 311,000. So 2007 would be 17 years after 1990, and then we have a 311 for the output. Now let's calculate the slope, but let's keep track of the units. So in the slope, we're going to take y2 and subtract y1, so that would be 311 minus 370, and we'll divide that by x2 minus x1, and that would just be 17 minus 0. And when we do that out on a calculator, we'll get our answer for that, and that comes out as a decimal to be negative 3.5. I'm going to round it off to negative 3.5. But the question is, what are the units on this number? Now, let's think about the y units. This 311 and that 370, what are they measuring? It's thousands of people. Okay, so the y units would be thousands of people. And what about the 17 and the 0? What are those measuring? Well, those are years. So the units in our answer will be 1,000 people per year. So 1,000 people per year. Now the fact that this is a negative slope, you see it's a negative 3.5, shows us that it's decreasing by 3.5 thousand people per year. So Pittsburgh's population is decreasing at 3.5 thousand people per year on average over that period of time. Now this would be an average rate of change because probably the number of people that the population changed by each year would vary a little bit. In order to be exactly linear, it would have to be exactly the same year after year. And then it probably fluctuates a little. But on average, it decreases by 3,500 people per year over that period of time. So that's an average rate of change. Now sometimes we're given a rate of change, and that can help us determine a model for a given situation. For example, the atmospheric pressure at sea level is 1 atmosphere. ATM is the abbreviation for atmosphere and is the unit that measures pressure. But underwater, the pressure increases by 0.0303 ATMs for every 1 foot increase in water depth. Let F of D be the water pressure at D feet. Now, this number right here, the 0.0303, is really a rate because it's saying the pressure increases by 0.0303 ATMs for every 1 foot increase in the water depth. That's really a slope, and since it's increasing, we know that would be positive. So the slope in this case is 0.0303, and that would be ATM per foot. So let's find an equation for F of D. So F of D represents the pressure at D feet. And we know that would start at 1 because that's the pressure at 0 feet, meaning at sea level, 0 feet deep. And then the pressure is going to increase by, so it's going to get greater, so we'll add 0.0303 for each foot of depth. So we'll multiply that by the number of feet of depth. Now, what's the pressure at a depth of 1,943 feet? This is actually the deepest point in Crater Lake, which is the deepest lake in the United States. Well, the depth of 1,943 feet, that would be D. So we're evaluating F of 1,943, which would be 1 plus 0.0303 times 1,943. And that comes out to be 59.9. And since that's the pressure, that would be measured in atmospheres. So ATM would be the unit on that answer. Okay, let's look at another example. The number of U.S. patent applications was 241.3 thousand in the year 2007, and it's increased by 10.9 thousand per year. Predict when there will be 320,000 applications. Now, notice in the information that we're given the initial amount. In other words, in the year 2007, it tells us that there was 241.3 thousand in that year. Think of that as kind of your starting point or your initial amount. And then it says that it's increased by 10.9 thousand per year. Now, the fact that that's per year, that shows us that's a rate, or really the slope. So let's define our variables. T is the independent variable, the number of years after 2007, and P would be the dependent variable, which is the number of patent applications in thousands. So we want a model, we want to generate a model from this information so that P, the number of applications for patents, let's put the initial starting value first, which is 241.3, and then it says it's increased, so it's going to be plus because it's going to get bigger, by 10.9 thousand per year. So you'd have to multiply that times the number of years, so times T. Now that we have this model, we can actually make the prediction. We're supposed to predict when there's going to be 320,000 applications. So that 320 would be the number of patent applications. So that would be plugged in for P on the left side of our equation. And then we'd need to do a little algebra and solve that for T. So first we'd subtract 241.3 from both sides of our equation. And that comes out to be 78.7 equals 10.9 t. And then we'd have to divide both sides by 10.9. So if we take 78.7 and divide it by 10.9, we will end up with about 7.2. I rounded that a little, but roughly 7.2. And so that means that 7.2 years after 2007. And so if we add 7 to 2007, that would be the year 2014. So it would be during that year 2014. Now in this next example, the model is given to us, and we're going to try to find and interpret the slope. So the function p equals 0.77t minus 43.18. So here's the model. Models the percentage of births outside marriage in the U.S. t years after 1900. And our job is to find and interpret the slope. Now, this model is of the form y equals mx plus b. Okay, so the slope is that number m, would be 0.77. So we'll write that down as the slope, m equals 0.77. Now what about the units on this slope? Now the independent variable is t, and that's measured in years. It's actually years after 1900, but it's in years. And the dependent variable, I'm abbreviating that, dv, is p, and that's measuring the percentage. So that's a percentage. So the slope is going to be, remember, always in y units per x units. And the dependent variable is your y, and the independent variable is your x. So it would be percentage per year. So we could write that as our units. Percent per year. Now let's interpret this. First of all, this slope is positive. So that shows that the percentage of births outside of marriage is increasing. And the amount that it's increasing by is 0.77% per year. So when we put this together, we can find our interpretation of the slope, which is that the percentage of births outside marriage in the U.S. is increasing by an average of 0.77% per year. Now there's one last thing I'd like to go over in this section, and that's how to perform what's called a unit analysis of an equation. And that's basically to show that when you have an equation like the one we have here, where we have p equals 0.77t minus 43.18, that the units on both sides of the equation are equal. And so let me show you how we can do that. So first, let me just rewrite that equation down below here. So p equals 0.77t minus 43.18. And we want to take all the numbers out, but just fill them in with what the units are for each thing. So, for example, let's start with this p here. Now this p stands for what? Percentage, and the units on that are percent. So we'll just write that as, I'm just going to use a percent symbol. Okay. Well, actually, now that I think about it, I think I'll go ahead and write the word right out, just so it's clear. So percent. Okay, so the units on the left side of the equation is just percent. Now let's look at the right side of the equation. Let's start with this number 0.77. Now remember, that's the slope, and that's a rate of change. So the units on that are the y units per the x units. The y units are percent, and the x units are years. So that's percent per year. I'm going to write that as a fraction, because the word per really means divided by. So it would be percent per, meaning divided by, year. Okay, and that's just the unit on that number 0.77 right here, because that's the rate of change. And that gets multiplied by t. Now, what's t measured in? Just years. So we multiply that by years. And then we subtract at the end this number, and that's going to be also a percentage. So we'd write percent. Now the key thing to notice here is that in this multiplication problem right here, that really what you have here is this year is really a year over 1. So that this 1 year is in the numerator and the other one's in the denominator, so they cancel. And so what you would have is percent equals a percent minus a percent. And the way units work when you're adding or subtracting, it's kind of like terms. Since both of these are percents, when you combine them using addition or subtraction, the answer is just a percent. So you get percent equals percent. And really what that does is it shows you that the units work out in this, so that the units on the left side of the equation are the same as they are on the right side of the equation.